Welcome to a new episode of From Classical Mechanics to Cold Atoms, where I try to give you intuition on how to transition from the classical to the quantum world. Let's get into it. In the previous episode, we learned that the de Broglie wavelength was the parameter that helped us know if we were in the quantum or in the classical regime, and then we could go from one to the other by decreasing the temperature of the atom or equivalently slowing it down. In order to slow the atom down, we saw that we could use a technique called laser cooling, where the atom absorbs a photon and later on it re-emits it in a random direction, and the atom ends up being slowed down a little bit. If this process is repeated many times, then the key points are the following. Because the absorption always occurs in the same direction, meaning that the kick that the atom receives by absorbing the photon is always going to the left, and then the spontaneous emission is random and therefore it averages to zero. After this process repeats itself many times, we end up effectively slowing down the atom and decreasing its temperature. However, there is a fundamental limit on how much we can cool down the atom or slow it down, and this is given by the recoil temperature, which in this case is about 1 microkelvin. This temperature corresponds to the temperature or energy that we're dealing with, which is the one from the photon. We can intuitively understand this by thinking that all the energy changes done during the absorption and spontaneous emission of the photon are in units of the photon energy. Therefore, the atom cannot have an energy that is lower than this quantity. Since a temperature of 1 microkelvin is not in the quantum regime yet, we need to resort to something else to cool the atom further down, but there is always hope, of course. And to surpass the fundamental limit of the laser cooling, we're going to use another technique which is called evaporative cooling, which is going to be the topic of the next episode.